Hello, today I'm going to talk about complex numbers and few stuff that you need to know um, to study them. At first I'm going to try to build all the science that is under it. So let's draw a line simply like that. You have a line. It would be better if it was in black. Uh, black. So you draw a line and you put all the numbers. So you have 0, here you have 0, you draw another, you have 1, and so on. And so on until infinity. So this half line here is called the positive reals. So it includes all the numbers between 0 and 1 and so on until infinity. So it includes all the reals between 0 and plus infinity. Usually when you learn them, you first learn about 0, 1, 2, 3, etc. And then you learn about numbers that are in between. Then you might know about uh, another space like this. You have you have a 0 in the middle, and you have negative numbers and positive numbers. This one is called the reals. So you have the positive reals, the negative reals here, here, and the positive reals here. You can notice that the intersection of both spaces are 0, and that will be quite important for the next part. Let's start another. Okay, but what if we built a space that were defined in another way? So imagine you have a line like this, as seen previously, and then you have your 0 here, and then you decide to build it on a space that is orthogonal to the reals, so something that doesn't look at all what it's like what it could be. So the property that we will give to this is that you can write all numbers as a sum of um, a real and another element times another real. So you have z that is in this plan, and a real on this axis and b a real on this axis, timed by I, a constant, that will define this space with the property that it's orthogonal to this space. And actually, the first property that we can write is that we notice that I squared equal minus 1. It's the property that defines this space. So what we say is that if you have one number here and that you square it, so you apply the transformation that is rotation of this side, and so I just rotates it from 1 here, so 1 is here, I is here. If you apply the transform of rotation once, then once again you find minus 1. So that's the property that builds that. So we have the property that you can write all the complex numbers as a sum of as a sum of a real plus I times another real. So we can write z as a plus y times b. But you can also define any space on the complex plan, for example m as here some number a and here some number b. But also you can define it in another way. So you draw a line from the origin 0, 0, 0, and then you take the angle here and you take the ray of this line, the ray of this line. So you can rewrite as an angle as a transformation of angle times a ray. So you start from here, you start from 1, then you multiply by the ray of this, so you get something like this. So something like this that equals to hair, so the length here. And then you apply the rotation, so you do this transformation. But however, this doesn't seem really well defined. So we take the exponential and we extend it to the complex. So this is the function exponential. For reals, you have the property. For reals, you have the property that a times b equals Oops, that's false. Exponential y plus b equals exponential a times exponential b. So we'll use that property. So you'll get that you can write as exponential y theta with theta and angle times r. So you extend it to the complex so that you can already split a complex number as a sum of both real and complex. Then if you add the I, you get this. So you have a real exponential and an exponential with an imaginary number, so a number on this axis. So you are pretty much screwed if you can't define it. So, oops, I can't. Can I please? No, I can't. Go back. Okay. So I'm going to do another graph with the axis. Oops. With the axis. Okay. So what we will define is that the angle here, theta, is an angle here, and the exponential y theta applies to the transformation of rotation. So we have that property. Now we can build pretty much everything we want. So for example, if we take any number on the plan, you can quickly see what will squaring it do. For example, the ray, so let's call the ray r, and the angle theta here, the angle is theta. Okay, so you have the angle theta. If you square it, you have the definition, the r that will be multiplied by itself, because the transformation of scaling from 1 to r will be applied twice. Oops, will be applied twice. So you'll go from 1 to r and then from r to r squared. So the squared will have a ray that doubles, which is normal. And for the transformation of rotation as well, it will apply twice. So you'll get something that rotates from the angle theta as well. So you have another transform that equals almost theta, and the ray equals r squared. That I don't have any. Oh yeah, maybe somewhere like here. Well, no, I don't have enough place to place the point, but it doubles. Okay, so now about the roots. Oops. What you may know is that the root of a positive real uh, is in the solution of the equation um, y y to the power n equal x implies y equals to the nth root of x. That's true for positive reals. So actually we know how to calculate that with computers. So what you get is that you have some positive real uh, that I will call r, and then you have a nth root that is um, that is uh, not only smaller, but you have the nth root here n of r, and so we know how to calculate that, but however we have no idea what's on this part, and actually we have no idea what's on this part as well. Well, see, um, we don't know what are on all these parts, and we only know what's on this line here. We have no idea what's on this part and this part. So uh, we will build in the complex plan a definition of the roots, and um, actually we will not start by defining it in the negative reals, but we'll start directly to extend it to the complex. So as we said earlier, when you square a number, you apply the transformation of the ray, and for some, and luckily, the ray is always positive because you can't have a negative ray. For example, if I try to do that, if I try to think of a negative ray, so this, but on the other side, what will happen is just that you have a theta that is either defined like this, or so you can measure it like this, but you'll always have a array that is strictly positive or zero. But okay, so you can actually think of that, and however we have this part that we know how to get the nth root, but we have the part of the exponential, and actually as a property, um, if we apply, I'm going to copy that, the nth root of exponential I pi is exponential I pi exponential theta. Wait, I'm not going to write it like that. How can I say it? No, what I want to say is that you have exponential I times, it's kinda hard, I divided by n, because you apply the modification n times, and you want to find the result of 2 pi k plus theta. So what this means is that, oops, wrong operator. What shit. What this means is that you have an operator. If you apply this transform once, you'll get 4 pi. Well, you'll get this twice. Then if you multiply by this number again, you get 3, then 4 until n. And once you have applied n times this, you'll get n divided by n, and you'll get I 2 pi k plus theta. And actually exponential I 2 pi k with k k in double z, so the positive or negative integer, and you'll get, if you apply it n times, so I'm going to power it to the power n, you get this, that equals to exponential n to exponential I theta. And as I said earlier, exponential I 2 pi k, with k an integer, is 1. So you have this, and we can actually visualize it. So imagine you have something 2 pi k. So if the angle is 2 pi or a multiple of 2 pi, you'll just flip all the way around. So an angle of 2 pi will be like this, and you'll just get back from the start. And at the same, for a negative number, you'll just get an angle of pi. So this is very convenient. And as well, we can get the property that y equals exponential I pi on 2, because if you apply a transform of rotation of pi on 2, you'll get this transformation, and you'll start from 1 to pi on 4. Okay. Now I guess we can start with an exercise that is very, very, very easy. So let's get this. Oops. Let's get this polynomial. Sorry, plus y equals 1. So this polynomial is actually very interesting because um, it gives very interesting stuff about the complex number, and it's a must know to start the study of the complex. Okay, so what will a student that didn't understood what I said do? To solve this, we'll try to calculate delta. Delta with delta a discriminant that equals to b squared minus 4 times a times c. B is 1 minus 4 equals minus 3. So he'll get a negative discriminant and say that it's negative, so there are no roots. However, we are in the complex plan, so you can't do this. If you do this, you are screwed. So to solve that, we'll get the roots. The positive root equals to minus b, which is 1, so minus 1, plus the square, plus y times the square root of delta, and all of this divided by 2, not divided by 2, divided by 1/2. This is the positive one, and obviously we'll get the same result, more or less the same result, with the negative root. Okay, so actually we'll get oops, where's my sign? Okay, so what we'll get here is square root of 3 and square root of 3. That's not very helpful, and with that we are not like very, very sure of what it does. So let's start from another thing. I call a number, it doesn't have really a name, let's call it, well, it has a name, but if okay, I'm going to start to call it j. J equals exponential y 2 y divided by 3 2 pi. Okay, so I set this number. Then what we notice is that what's inside the exponential is strictly imaginary, so it's a rotation. There is no ray inside it because it's not plus a real, not plus a real. It's only that. So the ray of this is 1, and we just have a rotation of the angle 2 pi on 3. So let's draw it. So we know that 2 pi is a rotation that doesn't do anything. So we'll divide the pi, the circle on 3 equal stuff. So we'll get something like this, with the angle here 2 pi divided by 3, and here 4 pi divided by 3. So what we notice is that when you'll apply j squared equals exponential 4 pi I divided by 3. So we'll get this at first, then we will rotate again, so we will get to the 4 pi on 3. So we'll get to this. What we notice is that if we sum j plus j squared, we'll get we'll get 1, then 2, then we'll get to 1. Oops, here was a mistake. Okay, I did a mistake earlier, it's minus 1. Okay, let's recalculate the delta very quickly. Oops. Let's recalculate the delta very quickly. I said minus b minus 1, oops, 1, minus 4 times 4, see, plus 5, oops, what am I doing, squared, b squared minus 4ac equals 5. That's not the result I'm supposed to get. Okay, sorry. I thought I had a problem, but in fact what happened is that just I forgot that these could actually be split, as I said earlier, as a factor of exponential and exponential of an imaginary part. So yes, as I said, if you calculate the module, you'll get 1 times exponential times I times 2 times pi times 1/3, and which is exactly what I wanted, and I didn't have to do all the stuff I did. Okay, and the other short solution you'll get is actually this. So the solutions we get from solving this is actually, so sometimes it's just easier to solve all of this with the equations. So what we'll get is j squared plus j plus 1 equals 0. Yay! Also, interesting properties. If you calculate j to the power 3, you'll get 1. So j is a third root of 1, of the unity 1. So it's one of the solution. Also, what we can get is j squared equals minus j. We can get it pretty easily just by adding pi on 4, and I think that's it. Oops, that's a mistake. Okay, so you have this, so the solution is like this, and as we can see, it's convenient with the complex to solve this. So what we can generalize is that one of the nth root of a number z, oops, not square root, the nth root, the number z equals uh, r times exponential I theta. R is called the modulo, theta is called the argument. We can split that up like this, exponential, and the exponential can get out of the way. Theta plus 2k pi. Okay, so we have the solutions to the nth root of all of this. So yeah, that's it. And what can we say? We have all of this. If you want a harder problem, here's something else. Partial, how that's called? Partial squared of f divided by partial t squared, with f a function of t, plus partial f of t divided by partial t plus f of t equals sinus of t. So you can solve this. You have two tips. The first, that this thingy looks like this thingy, and also you can guess that sine of t equals 1 divided by 2i exponential of exponential exponential 2 why this I t minus exponential minus it. Yes, like this. Okay, so I guess that's pretty challenging, and good luck and have fun.